We use the terms phenomenological and physics-based once or twice in the previous slide. So let's just recall what those are and how they're different. So we have a set of questions. Is the definition of satisfactory performance by our item available in terms of the physics of the problem? If so, do we know the randomness is involved, including is there any time dependence issues there? So if the answer is no, then we really cannot do much. We have to observe failure, perhaps test many identical samples of that unit, and then observe failure, estimate time to failure, and so on. So that's what we called phenomenological approach to reliability. But if the answer is yes, then we would go for a physics-based reliability problem, especially because in the types of units that we are interested in, structural components and systems, we do not have the ability in most cases to do many tests on nominally identical samples. So we are almost required to look at the underlying mechanics of the problem and derive failure from the underlying mechanics, including how the elements, the component failures come together to define system failure. So that's what we mean by physics-based approach to failure, and obviously for structures that's almost always the way forward. Then we also mentioned systems. So let us again recap how we defined what a system is as opposed to a component or an element. Is the item of interest, is it made up of two or more units that are logically and physically connected, so that the item's performance, whether it's functioning or not, whether it's failed or not, can only be described in terms of the unit's performance. So that is the key part. If I am able to define the system's performance just with one condition, then it doesn't matter how large the system is, how complicated the system is, I would treat it as one component, one element. But if, on the other hand, I have no choice but to describe the system's performance in terms of its in terms of its constituent units, then we have an element or component reliability problem, provided we have data or a model of failure of these constituent units. In that case, each such irreducible unit is an element of the system, and we just need to know the logic, how they come together and build up the system. And if it's not, it's an element reliability problem. We use the word element and component interchangeably, and we have looked enough of these. So the focus of this week is system reliability problems. So which means that we know the element failures, we have descriptions, definitions, criteria for element failures. And for our case in structures, we typically call those limit states. So let's now see how the system comes together in terms of its element limit states. Recall that we defined reliability of an item of interest as the probability that it serves its purpose satisfactorily over the entire duration of interest, 0 to t, under given conditions. So this particular item of interest occupies a logical or physical domain, omega. So if we fix a particular location, if it's a physical domain, a particular location x, or more generally, if it's a logical domain, some particular identifier tag of that domain, then we can define failure at that location or at that identifier as some function, and in our case a physics-based capacity demand-based function, safety margin function, going out of the safe set for the very first time. So that gives us the concept of a component or an element, that it is an item of reliability that describes one single failure mode at one critical location, or more generally at one identifier in the logical domain. So for that component I, we have already defined the state random variable, the indicator function, the binary random variable, that if it is if the safety margin, if the margin function has gone out of the safe set any time during 0 to t, so it's failed, its value is 0, otherwise it's up and its value is 1. Now the system comes together in terms of its constituent elements through the structure function alpha. So alpha is a function of all the individual component i's state functions, and likewise if the system is up at time t, it's 1, otherwise it is 0. Now when we have a physics-based approach to failure or mechanics-based approach to failure, we have function g, which is equivalent to the margin function m that we were talking about, that if that g is less than 0 for that component, we have failure. If that g is non-negative, we have safe performance or acceptable performance, and the line or the hypersurface separating these two regions is the limit state equation. So we express equivalently whether the component is up or down in terms of the sign of the g function, the limit state equation. Now the probability of failure then brings all of these individual component limit states, how they come together through the structure function. If we are able to know that, if we understand the underlying mechanics of the system, then we can describe failure of the system in terms of its element failures, and we can estimate the failure probability of the system in terms of all the randomnesses involved. Now, so putting everything together, we are talking about structural reliability and structural system reliability this week. So we have a mechanics-based formulation, which is essential because we do not have an abundance of cheap identical samples to test. So we cannot directly get the time to failure, for example. So we need limit state functions. We also need to consider all the uncertainties. There are many degrees of freedom. There are many failure modes. And these systems are non-repairable in nature. Again, this term repairability is a technical term. It basically means that the item of interest cannot just be taken offline and replaced by a completely new identical replacement. So our structures are not like that. So from that definition, they are all non-repairable. We cannot afford to just pick them up and replace them. And all our systems have this property of being active redundant. There is load sharing, there is load path dependence, and if there is unloading involved, it doesn't have to follow the loading path. And then if there is sequence of failures, then there is load redistribution, and then some of these sequences may be more likely and others may be less likely. So we need to understand that behavior as well. And near failure, our structures start behaving in a nonlinear manner. The material starts behaving in a nonlinear manner. So All of these things coming together, including all the randomnesses involved, bring in several degrees of challenges and interesting aspects to this particular branch of reliability, which is structural reliability, and in particular structural systems reliability.